G'day, Mr. Bennett here. Now, today we're going to be looking at balancing our equations. Alright, so it's really just a matter of making sure you balance the atomic number and the mass number. Alright, so when we're doing these things, what you'll be given three of the either reactants or products, and then you'll need to work out what the third one is. Alright, so let's do these ones here that I've just done for you. Alright, so if we're looking at the atomic number, we've got 4 plus 1, which means that that's going to be 5. So on the other side, it has to be balanced to 5. So we've got 2 there. That means that this thing over here must be 3. Now looking at the mass number, on the left-hand side, or the reactants, is 10. 9 plus 1. So therefore, on the other side, it must be also adding up to 10, because that's 4. That has to be 6. Okay, so that's that thing there. Now we can go to the next step sometimes, and we can also look at not telling you what the actual element is, right, the atom is. So here we've got obviously the difference between the reactants and the products is going to be 2. The difference between the mass and the of the reactants and products is going to be 4 there. Okay, so this one here is actually equal to helium. We know helium is 2, 4. Alright, so the next one over here, we've got nitrogen plus helium. Alright, so we've got 7 plus 2 is 9. On this side of here, we've got 8. Excuse me. So that has to be 1. And then over here, we've got 18. And over here, that's 17. So that has to be 1. So that would have to be a hydrogen atom that would be getting there. Now, sometimes you know what the atom is, but again, you have to balance that out. So over here, we've got 7 on this side and 6 on that side. So there have to be 1 there. And then on this side, we've got 14 and 12. So therefore, that have to be 2. So again, I simply just balance out the numbers. So these sort of questions, I think, are pretty easy. Now, with hydrogen, there are 3 isotopes of hydrogen, or common ones. So that's just hydrogen. And then we have this one over here, which is H12. That's called deuterium. And then the third one, which is H13, and that's called tritium. And these are quite commonly used when we start looking at the nuclear reactions and so on. Alright, get the idea there? So we're adding and subtracting, we're making sure we're balancing out the atomic number and the atomic mass with these. Now, I just want to talk to you about the idea of how the atom actually exists. And there's something that we have to understand is, alright, so when we're looking at the forces here versus the distance, okay, so this is actually the distance, and this is distance between nucleons. Right, and this one over here is the force. Now, if you think about the nucleus, inside the nucleus we have protons and neutrons. Now, neutrons have no charge, where protons have a positive charge. Now, when we did our electric fields topic, we know that when we have 2 like charges, they want to repel each other. Right? So that's what actually does happen, is when we have 2 like charges, they do want to repel each other. So therefore, for these protons to be in the nucleus, there must be a very, very strong nuclear force that holds them together. Right? And that's true. So the force between protons and neutrons and protons and neutrons is equally the same, no matter what they are inside the nucleus. Now, the thing about this nuclear force, it only acts over a very, very short distance. So if when we start looking at the distance between nucleons, we have this strong nuclear force that goes like that. And then when we have basically, when we're looking at the force of attraction, so this is what we call the strong nuclear force. That only acts over a short distance. And then when we start looking at this thing over here, this is the electrostatic force. force, and we know that basically works with 1 over r squared, doesn't it? Okay, so that's the Coulombic force that we're looking at there. So there is a certain distance once the nucleus gets too big where the electrostatic force will overcome the strong nuclear force and the nucleus will be split apart. And that's what we generally see when we start looking at the bigger atoms themselves, like uranium and so on. The electrostatic forces actually start taking over, and these things naturally or spontaneously start to decay. But when we have very, very small atoms, like carbon and those things, very strong, the strong nuclear force is much stronger than the Coulombic forces, so those things are very, very stable. Alright, so do you understand? Hopefully you understand the concept that the strong nuclear force only acts over a very short distance, and the force between protons and neutrons is no different from each other. Alright, so it treats them exactly the same. The only real difference between a proton and a neutron in this case is that the proton has a charge and the neutron doesn't. So that's the strong nuclear force concept. We call this particular force, has a special name. In this particular case, it's called the binding energy. Alright, so the binding energy. So when we start looking at chemistry, what happens in chemistry is we have energy that's released by electrons being emitted from the atom. In the case where we start looking at the nuclear stuff, alright, the energy that we get from looking at the electrons being emitted compared to the energy that happens when you start splitting your nucleus. So obviously if you split the nucleus, that's going to be equal to the amount of the binding energy that you're going to release, and that energy is much, much, much greater. We'll do some calculations to show you how much greater the energy is there than when it's actually released. Now it brings us on to the most famous probably equation in physics, and even people who don't do physics actually understand this, or don't understand the equation but they know it. Equals mc squared. So we know that m is equal to the mass defect, and we know that c is equal to the speed of light. And we'll do some calculations to show you the amount of energy that's actually released when these particular atoms sort of undergo radioactive decay. Alright, so anyway, that will do it for today in terms of looking at the key concepts. So the key concepts again themselves, alright, we're balancing equations. Certainly you'll see one of these or a couple of these questions in the exam. So all you're balancing is the atomic mass number and the atomic number. And then we talked about the concept of the strong nuclear force, or the binding energy that binds the nucleons together inside the nucleus. And so therefore, this is a really key concept. It only happens over a short distance. And that's why we find massive atoms. When we start looking, generally anything over the 83 atomic number is basically starts to have this electrostatic forces overtaking, and so those things will spontaneously decay. Alright, so that particular size is quite critical, and that's to do with the size of the protons and the neutrons. Obviously when you're getting 83 protons in there, you've probably got in the order of 120 neutrons, and so therefore the nucleus is actually getting quite big. Alright, so that's what we need to be looking at, and we'll talk about that in one of our later videos. Alright, I'll talk to you in class.